The next two lessons in our equilibrium unit are going to focus on problem-solving methods that will assist you in all types of equilibrium problems in the next 3 units. The first lesson here on this problem solving is to address something called a reaction quotient, which is related to the equilibrium constant. The second lesson attached to this will be on how to solve icebox problems. So up to this point, you should already be able to write a mass action expression, and you should also be able to manipulate mass action expressions to calculate K and calculate concentrations at equilibrium. By the end of this first lesson, you're going to be able to use reaction quotients to determine if a system is at equilibrium. The lesson following this, you're going to be using ice boxes, which is a problem-solving method, to calculate species that are not at equilibrium. So this concept of reaction quotient, or capital Q, is really the same setup as an equilibrium expression. It's just the term for a calculation when we don't know if the system is equilibrium or not. So if a question specifically says a system is at equilibrium, then you'll use the letter K. But if it just says, oh, you're given a particular system and here's some concentrations, you cannot assume that it's at equilibrium, so you cannot use the letter K. You have to use this letter Q. So basically what you do is you would substitute you would put in the concentrations, products over reactants, just like you would do with an equilibrium expression, to calculate this letter Q value, and then you would be comparing it to an equilibrium constant to determine, is my system at equilibrium or is it not? It depends on the value of Q when you compare it to the value of K. So the idea here is if you calculate the value of Q, which again would just be your products over your reactants, if the value of Q is equal to K, that means then yes, your system is at equilibrium. The forward reaction and the reverse reaction would keep proceeding at the same rate as they were. If you calculate Q and it's greater than K, that means that too many products are present in that system compared to what there should be at equilibrium. So the system would favor the reverse reaction to establish equilibrium. So think of it this way, that if you have Q and K, and Q is the bigger number, the reaction is going to proceed in that reverse direction in order to establish equilibrium, to reduce the value of the numerator and make it equal to K. If, on the other hand, your calculated Q value is less than K, that means you have too many reactants present in your system, again, because you have products over reactants. So if your Q value is small, that means your denominator is a large, which means you have too many reactants. Your forward reaction would occur at a faster rate than your reverse reaction until the system reaches equilibrium, and at that point, Q would be equal to K. It seems kind of silly to do this, but it is actually useful to determine if a system is at equilibrium or not, and then, what kind of further calculations can be done from that. So here's an example, three steps here. For the synthesis of ammonia at 500 degrees Celsius, you have the equation here. The equilibrium constant, so the K value, is 6 times 10 to the negative 2. Predict the direction in which the system will shift to reach equilibrium in each of the following cases. So we are given concentrations of ammonia, nitrogen, and hydrogen in 3 different scenarios. So what we need to, we're not told that these are in equilibrium, we're just given these concentrations. So we need to calculate our Q value and compare it to this given equilibrium constant to determine if our system's at equilibrium or not, and if it's not, which way would the reaction proceed in order to achieve equilibrium. So the first thing we need to be able to do is write our equilibrium expression. So our equilibrium expression would be products, which would be the concentration of ammonia squared divided by our concentration of nitrogen times our concentration of hydrogen cubed. So now we're just going to plug in these concentration values and see what we get for our Q value. So for the first one, it would be 0.001, and that would be squared, divided by 1 times 10 to the negative 5th, times 0.002, and that would be cubed. When you calculate this, you get 1.25 times 10 to the 7th power. a very large number. So we compare that to K. So in this case, our calculated Q value is greater than K. So that means our numerator is too large. There's too many products. So what's going to happen here is the reverse reaction is going to happen at a faster rate than our forward reaction in order to establish equilibrium. For the second example, we have 2 times 10 to the negative fourth for our ammonia squared, divided by our nitrogen, which is 1.5 times 10 to the negative fifth, times our hydrogen, 0.354, and that would be cubed. When I solve that one, I got 0.06. So in this case, 0.06 is equal to our equilibrium constant. So with these concentrations present, our system is at equilibrium. The concentrations will remain constant. There is no favorability for the forward reaction or reverse reaction. They're going to proceed at the same rate. This last example, we have 1 times 10 to the negative fourth. We'd square that, divide that by 5, and then times 0.01, and that would be cubed. So when you calculate this, I got 0.002. So in this case, our Q value that was calculated is less than the equilibrium constant, which means our denominator is too large, our reactants are too plentiful, so the forward reaction is favored, and will proceed at a faster rate than the reverse reaction until both reaction rates are equal. So at this point, you should just be able to plug values into a reaction quotient expression, calculate Q, be able to compare it to an equilibrium constant, and then determine which direction, if any, your reaction would be favored in order to establish equilibrium. In the next lesson, you're going to be shown how to solve ice problems, which are useful in all aspects of equilibrium problem solving.